Hello, my name is Iken Kim, and I'm a graduate student doing Master in Data Science program at Maryville. And today I'll be doing a short presentation on a project that I've been working on, which is estimating the ultimate claim values of workers' compensation insurance. And I would also like to thank Dr. Robbie Bean for his supervision, help, and guidance on this project. We'll start off with some definitions of key terms. Workers' compensation insurance is an insurance coverage that provides for medical expenses and lost wages to employees who become ill or injured in the course of their job. It also includes coverage for death benefit families if the worker is unfortunately killed while on a job. The ultimate claim values represent the total sum of payments required to cover all losses and loss adjustment expenses associated with the claim. Most of the time, the insurance companies do not know the exact ultimate value of the claims because claims can take years to develop. Depending on the severity, an injured worker may take months or even years to recover. And even after recovery, a worker may still incur regular medical expenses throughout their lifetime. Besides, inflation also increases the medical costs and creates more uncertainty around the ultimate claim values. And in this project, we are using data provided by the Actuaries Institute of Australia, the Institute and Faculty of Actuaries, and Singapore Actuarial Society. It is a synthetically generated dataset of workers' compensation insurance claims. And this dataset includes demographic information on the injured worker, such as age, gender, marital status, number of dependents, weekly wages, number of hours worked per week and per day. It also includes details on the accident, including the date and time of the accident, the date the accident was reported, brief claim description, and initial estimate of the claim cost by the insurer. There are a total of 90,000 claims in the dataset, which was split into training and test set by a 60-40 split. And our goal is to use the information from the training set to train our models and to predict the ultimate values on the test set. The result is evaluated using root mean squared error, and this metric penalizes large errors between predicted and actual values. And before I start the training models, I did some data cleaning and performed some exploratory data analysis to understand the relationships between the variables. I first identified any missing values in the dataset, and it turns out there are a few observations with missing marital status, and I replaced those missing data with a category called unknown. And we also have the date and time of the accident in our database. So I performed some feature engineering to extract the year, month, and day from those columns. And after getting the data ready, I went ahead and explored some of the relationships between our variables. And here I am just showing a few of the graphs. Top left graph here shows the distribution of age of the injured worker. It is slightly skewed, as you can see. The majority of the workers are between 20 to 30 years old. The bottom left graph here shows a box plot of a log transform response variable by gender. And by the looks of the graph, it does not seem like the response varies significantly by gender. And the right graph here is a scatter plot of some of our numerical variables, just to get a little more insights into our data and the relationships between the features. And as I was exploring the data, I realized a few small challenges. And one of them was that the response variable is highly skewed to the right. And most of the workers' comp claim usually have very small values, and there are some rare cases where claims values can get really large. So as you can see on the left here, the graph shows a histogram of the ultimate claim values, which is our response variable in the training set. And you can see that most of the claims are actually under $500,000, but there are some claims that can reach up to $4 million. And then we decided to perform a loss transformation on the response variable. And the right graph here shows a histogram of after the transformation and the ultimate values. And this transformed variable now looks a little more normally distributed than before. The second challenge that I was facing was that the date and time of accident and report dates were creating too many features in a dataset. And one of the things we calculated from our exploratory analysis was the correlations of features with a response. And as you can see on the right chart here, we realized that the accident days as well as the report days actually have very low correlations with a response. So we proceeded to eliminate those features from our data. And this reduces the number of features and improved our model training time. And after getting our data ready, we then explored several models to predict our response. The models that I have considered include the ElasticNet model, decision tree, random forest, neural network, gradient boosted tree, and ensembles. And for some of these models, I also perform hyperparameter tuning using a grid search technique with cross-validation. And after finding the best model, I then compare the scores against among each of the models to get the best model. And I'll illustrate the modeling process using the random forest as an example. So before specifying the model, I actually had to first perform some feature scaling and encoding. So I divided my features into categorical and numerical. And you can see at the top here, the categorical features consist of gender, marital status, part-time or full-time status, the accident year, the accident month, report year, and report month. For numerical features, we have age, the number of dependent children, number of other dependents, weekly wages, hours worked per week, days worked per week, as well as the log of the initial claim values. For numerical variables, I used the mean max scalar to transform the values into a range between 0 and 1. And then for categorical variables, I first used a simple imputer where I replace any missing values with the letter U, which stands for unknown, and then perform one-hot encoding on the variables. So after getting the features ready, I then specify a random forest model and listed the parameters that I like to test, as well as the different values for those parameters. So in this example, I am testing different values for n estimators, the max depth, and minimum sample sleeve. So for each of the parameter value combinations, the random forest is run, and the grid search technique is used with a 5-fold cross-validation to find out the best parameter set. And the second half of the codes shown here demonstrate the process of printing out the best parameters along with the validation scores. The score is then compared against the score of other models, and then the model with the highest validation score is our best model. So it turns out that the best model from the list that we've shown in the slides before, the best model turns out to be random forest model with the following parameters: the max depth of 10, minimum sample sleeve of 8, and n estimators of 100. We then use this best model to generate predictions on our data set. And on the right here, you can see a screenshot of how the predictions look like. For each claim, we have a claim number, and for each claim number, we have generated a prediction of the ultimate claim value for that claim, which is the goal of our project. And our final test score using this model was 24,016. This was the root mean squared error of our predictions of the test set. And that is all I have today. And thank you for your time, and thank you for listening to my presentation. Thank you.